In example 7.2, we're going to see an opportunity where we can use an average rate of change calculation in one of the natural sciences. And the natural sciences do adopt many of the mathematics concepts that are developed, and physics won't exactly call it average rate of change all the time. They have another name for it. So we're going to see that here in example 7.2. It says if an object is dropped from a high cliff or a tall building, then the distance in feet it has fallen after t seconds is given by the function d of t equals 16t squared, comma, t is greater than or equal to 0. So this statement after the equation, t is greater than or equal to 0, that is an inequality, which would be equivalent to the interval 0 to infinity. That represents the domain of your function. So physics doesn't always use the same notation that mathematics does. So remember, the idea behind a function is that you have to have both an equation and a domain to accurately describe a function. And this is the way that we have it described for us here. And we have both of them. We have the equation and we have a representation for the domain. So all the pieces are here. And then it says find the object's average speed. Now, average speed is not the way that we would normally talk here in a math class. That is definitely a physics concept. Speed, velocity, those are a physics concept. And what we would interpret that as is the average rate of change. And then it says specifically between 1 second and 5 seconds. So we are definitely doing an average rate of change calculation. That's going to be a rock. So that's the first thing I'm going to write down for this calculation is a rock. And according to our definition, the average rate of change is just a slope calculation. And we would normally say delta y over delta x. But since the variable in the equation is t and not x, I'm going to change the denominator to say delta t. But I can still certainly say that the numerator is going to be delta y. So if I think about this from the slope formula perspective, this would be the same as saying y2 minus y1 divided by t2 minus t1. So then I would have to decide what are going to be the values for t1, t2, y1, and y2. Well, I say I have to decide, but some of this is already decided for me. So it says between 1 second and 5 seconds. So that means I'm going to need to let t1 be equal to 1 second, and t2 is going to be equal to 5 seconds, which gives me half of my calculation, 5 minus 1, but I still need to have the corresponding y2 and y1 that are going to go with t1 and t2. Fortunately, we have an equation for that. So then, once I establish my t1 and t2, let's go ahead and calculate y1 and y2. So y1 is going to be equal to the function with t1 plugged in. So I'm going to plug in 1 into this function. In other words, calculate d of 1, and that's going to represent y1. So 16 times 1 squared, which is going to give me 16. And I'm also told in here that distance from this function is supposed to be measured in feet. So this is going to be 16 feet. I can do the same thing for y2. y2 is going to correspond with t2. I can calculate that as the distance at time 5. So d of 5, 16 times 5 squared, and that will eventually get us 400 feet for that calculation. So now I have y2, y1. Let me substitute those into my AROC calculation. 400 minus 16. That's going to give 384 divided by 4, which is exactly 96 feet per second. So the unit is feet per second because the numerator, which is the 400 minus 16, is 384, and those units were both feet, and then the denominator, which ends up being 5 minus 1, giving us 4, is in seconds, and so that's where we get the unit feet per second. And 96 feet per second is the average speed of this ball between 1 second and 5 seconds after it's been dropped.